And now we have a very interesting talk by Professor Briceño. He's from Universidad, Técnica, Federico, María, and he will be talking about splitting algorithms for solving composite convex optimization problems, asserting and new results. Thank you very much.
Thank you, Federico. Thank you for the invitation for giving a talk here, and everyone for being here. I will talk a little bit for a survey of mainly of one of the results and the algorithms that I have developed in my starting from my thesis up to now, but also other classical algorithms for having a kind of story of how the algorithms came to solving of convex optimization problems. The non-convex part will be not talked in this, will not analyzed in this talk. Then the idea is, well, talk about a little bit of the problem, the motivation of this problem, some technical properties of convex analysis mainly, and I split the talk in two parts. First one is algorithms 1, in which f is simple. We will talk about that when f is simple, if it's possible to take a gradient of the, have the gradient of the f, or if proximity operators can be computed. Then, well, I will talk a little bit further later. And the second part is which f is not simple but can be written as the sum or composition of simple functions, and how in that case we can exploit the intrinsic properties of each part. That's the main idea. And after that we will talk some perspectives on some things we are beyond the optimization, mainly monotone operators, and a little bit of some ongoing applications that I'm working on. Then that's the principal setting. The main setting is a problem P. We will talk problem P is just minimize in Rn a function fx, under the assumption that we have solutions. We will not talk about when we have solutions. We assume that we have solutions, and we will we're looking for an algorithm for finding a solution. Okay, here f, the main context is f is a function from Rn to R union plus infinity. We accept to the functions take the value plus infinity, mainly for having some constraints, for example. And we ask to f to be convex. Here is the definition of convex. We will discuss a little bit for the people who doesn't know what it is. Lower semi-continuous and proper. Proper is mainly that it's not always plus infinity. It's we are interested in problems which have some sense. Then that's two properties we will discuss later. And the function satisfies these three properties constitute the class gamma 0. All the functions in gamma 0 are convex, lower semi-continuous, and proper. That's the main idea. And examples of functions here, well, exponential, for example, in R, or in Rn, the norm square. And those functions, in the case of differentiable one, are like that in R. There is the definition of convexity. Mainly, it's if we take any 2 points here, you can, and you take a point in the middle, x sub lambda, you have that the evaluation of the function here is less than the same report from fx and fy. Then this one is less than this one. That's the main thing. Then all the convex function has a kind of have a kind of that kind of form. But for every xy, okay, then you can move it, and always you have that behavior. Of course, if you have not differentiability, but just continuity, you can have some functions like that. It's just the absolute value, or things like this one, which is 0, and after that it's just. But you have some here is differentiable, and in this point it's not. Okay, and this is another example of functions in gamma 0. And also you can have some discontinuous convex functions, and in that case, for example, that's the main example that we will discuss here, is the indicator function of a set, when the set is closed convex subset of Rn. In the case of R, that's the set, and we need to be closed, if not, it's not lower semi-continuous. Lower semi-continuity mainly discuss that if you have some function here and you have a jump of the function, you need to be the evaluation of the point x in which you have the jump has to be not on the top but at the bottom. Okay, that's the main idea, because the definition is that fx is a limit of yx the fy. Then you have the between the whole sequence coming to x, the lower value has to be, sorry, it's like that. The lower value has to be fx. Okay. Then mainly is that the epigraph is closed. Okay. Then that's why here we need, for this example, to have just those 2 points. If not, it's not lower semi-continuous. Okay. Then that's a main example that we will use here, mainly for having some constraints. Indeed, for example, if you have a convex function f and a closed convex set C, you can define a function like that will be also in gamma 0, in which in some set C it's fx in which it's convex, and plus infinity otherwise. In that case, you have the sum of 2 functions in gamma 0. If it's in gamma 0, and the indicator function is 2. Then in general, beyond that, you have that if you have 2 functions in gamma 0, the sum is also in gamma 0, and also the composition with a linear operator. When in our case we are in finite dimension, then just matrices. The composition also will be convex, and an easy example in which is just by definition you can have that property. Well, concrete examples of that kind of problem, or problems coming from the sum of functions, are, for example, lasso. It's a problem known in statistics, and the idea, and also in imaginary, and the idea is to approach the vector y, but with a matrix A going there. And A here is rectangular. Then between, we have tried that to approach AX to be y, but try to find the sparsest solution. Okay, the norm R1 allows to have a sparse solution in the sense that the vector has a lot of zeros. That's the main idea. That why you can have that, it's because the norm 1, it's like that. Well, depending on what's the value of the norm. And when you have some gradient or something, it's easy to have that kind of solutions. When you have, for example, if you minimize norm 1 subject to, I don't know, x equal y. It's not the same problem, but the idea is you minimize, it's easy to have sparse solutions. Then that's why that problem is important in imagery and also in statistics. Other problems in which you have many applications, it's constraint convex optimization. You minimize an fx over convex inequality and linear equality, for example. In all those settings, we have, yes? Yeah. Okay, no problem. Then you can, those 2 problems are in our setting. Well, what is the goal of this talk? Is to review some classical algorithms for solving P when F is differentiable. If this is differentiable, we are talking about gradient methods, or its proximity operator is easy to compute. In that case, we talk about proximal methods. I will explain what is it. In this case, we will say that F is simple, if we can compute even its gradient, or its gradients, or the proximity operator, it's simple. If it's not, we provide algorithms for solving P when F can be gradient as the sum or composition of convex functions, okay, or linear operators, where F and G are simple and the matrix L is just a matrix. and by exploiting the intrinsic properties of each operator involved. And we will give some connection between algorithms and optimality conditions, and some connections also between the convergence of the algorithms and properties of associated fixed point operators. We will see that algorithms can be seen, also some algorithms can be seen as a fixed point iteration of some operator which have nice properties. Okay, then we need some preliminaries. We will talk about function f will be strongly convex if, even if we subtract a norm square, we have also a convex function. And it's even more than a convex function because the norm square is already a good convex function. The subdifferential of a function in gamma 0, and we have some design here. For example, in the case in which you have the absolute value, the subdifferential is the operator that for each x takes all the slopes which are kind of gradient. Indeed, in the case of in which f is subdifferentiable, the subdifferential is just the gradient. Okay, it's a singleton gradient. But in general, in that point, you take all the slopes. Okay, for example, here the subdifferential of gradient of absolute value in 0 is just minus 1, 1. Okay, in that part it's differentiable, then you have just minus 1. And this part is differentiable, so it's just plus 1, and you have something like that. And here you take all of them. That's the subdifferential of absolute value. Okay, if it's differentiable, here you have only 1 point or something like that. But if it's not, you take all the slopes which are supporting the epigraph. The French conjugate of a function in gamma 0 is defined like that. We will not going too far in that definition, but the important thing that we will use in some part of the talk is that in that case the subdifferential minus 1 in the sense of set value operators is just the subdifferential of the French conjugate. And this one is important. It's the proximity operator of f will be used through the talk. The proximity operator for a y is to solve a problem, to find the solution of this problem. This problem has a unique solution because this is convex and this is strongly convex. Then you have only one solution for each y. That solution is proximity operator of y. Okay. Then, well, for the optimality conditions, you can have that the proximity operator can be seen as the inverse of that operator, the identity plus subdifferential. And indeed, it's single valued. In particular, one idea if f is the indicator function of a convex closed set C, here we have x just is 0 in C and plus infinity if it's not in C, and here you have just x in C of the minimizing on 1/2 of the norm square of x minus y. Then the solution of that is just a projection for y to C. Okay, then the proximity operator can be seen as an extension of the projection. Okay, but here you can take any convex function. That's the story about convex functions. But now I say that the convergence of the algorithms are related to operators. Then we need to review a little bit of fixed point theory. Well, the fixed T is the set of fixed points of an operator T which goes from Rn to Rn. It's non-expansive if for every 2 points in Rn the images are closer than the pre-images. Okay, you take 2 points here, x and y, and the Ty is closer than T. So this distance is less than this one. Okay, once you apply the operator T, it's less than equal or equal. Okay, if it's strictly less for every x and y, you have a contraction. So when there exists a row strictly less than 1, in which here which the distance is strictly closer the images. And it's averaged, that's an important operator also. The average operator, if it exceeds an alpha in which you have not that much as a construction, but you already have non-expansivity, yeah, with the square, but you have that term also that helps you to be better. It's better than non-expansive, but not that much as a contraction. And here alpha appears, and there's a lot of algorithms that satisfy that property. So most algorithms in which the operators associated satisfy that property. In particular, for example, PROX, which we have discussed 2 minutes ago, it's averaged with alpha 1/2. That's an example of those averaged operators. Of course, if you compose two non-expansive operators, you have already another non-expansive operator. Two contractions, you have also other contractions. And if you have two averaged operators, you can have another averaged operator with an alpha which depends on two alphas. Okay? Yes?
Does average imply it's a contraction?
Sorry?
Does being average implies it's a contraction?
No, no, not at all, not at all, not at all. Just non-expansive. Just non-expansive, but this one doesn't ensure the existence of that role at all. Yeah, you have an uniform role, but here there are some examples in which that can be not ensure an uniform role. Okay. Well, those operators will appear in the algorithms I will present later on. Okay. Okay, let's start with the first part, in which we have just a simple function f. The first case is differential. If we have minimized some differential function, we will assume a little bit more. It's not necessary. You have also algorithms in which, if the gradient is not Lipschitz, we are assuming that it's Lipschitz. Also, you have convergence, but with special steps. Okay, we will not discuss all the details, but we will assume a little bit more. You have convex differentiable, and the gradient is Lipschitz. In that case, Lipschitz is just that. Okay, there the xi doesn't need to be later less than 1. Can be any number, positive, of course. Then, if we have a kind of control of the gradient, you have the Lipschitz property. Optimality conditions, because of the convexity, we're always in the convex world. The optimality conditions characterize the solutions of the problem. Yeah, any solution of the problem P over there, it's equivalent at the gradient in that point is 0. Yeah, the idea is simple. You have a convex function because all functions looks like that, and that's the minimum, and well, the gradient should be 0. That's equivalent by just taking minus gamma, multiplying by minus gamma and adding an x, is equivalent to that for any gamma positive. And that's equivalent to x is a fixed point of an operator that I will write it as g gamma f, which is just x minus gradient of f. Because of the gamma, here's the gamma appears here. Okay? Then it's a fixed point of an operator. What are the properties of this operator? Well, we can find solutions. We are agreed that because of the characterization, we can find solutions of the problem via the fixed point of the operator. But the operator has to have the fixed point. Well, the gradient method is just the fixed point iteration of that operator. The gradient method is to take xn plus 1, this operator of xn, okay, and iterate that. But the thing is when that operator is good enough for obtaining convergence. If f is strongly convex, I remember you that the strongly convex is when you subtract a square, non-square, it's still convex. It's a very good convex function. If it's strongly convex and you have a parameter gamma which is small enough, depending on the beta and the xi of the Lipschitz gradient, then this function is a contraction. Then if you have contraction, you iterate a contractive operator, the Banach fixed point theorem ensures you unicity of the solution of the fixed point, and also the linear convergence. Then in that special case, you have a very good operator on which iterating you will converge very fast. Of course, it's a very, you have a lot of assumptions on F, and having strong convexity is too much. If it's not strongly convex, but still the gradient is Lipschitz, and gamma is small enough, small that constant, 2 over the Lipschitz constant, then that operator is not a contraction, but it's averaged. And if it's averaged, well, I will not do the proof, but if it's averaged, you can also obtain convergence of the algorithm, not necessarily unique in that case. That's why we are assuming existence of the solutions. Okay? If it exists, we will converge, and it's not linear as before. But I will take a look on that algorithm. Sorry? Yeah, it's usually slower. If you have no more than that, you have just not linear, but the best that you can have it's kind of 1 over k, or order 1 over k. But you have some acceleration schemes. Roberto has talked a little bit over that in his lecture, I guess. Not yet. Okay, not yet. Well, it's just for interesting the audience. Okay, next just say, okay, everyone here. Just advertising that. Then I want to discuss a little bit how this algorithm looks like. Imagine that's the level curves of the function f. That algorithm take xn. Imagine that you start an x0, I don't know where, but you start an xn. The gradient goes up. It's the direction in which it's the best, the highest slope. Then identity minus gamma f goes in that direction, opposite to the gradient. Yeah. Then here you can the xn plus 1, which is xn minus gamma gradient fx. Then they are going always in the greatest descent of the function. And from here you take again the same thing and go in the direction, go looking for that solution. Okay, that's the simplest gradient step. Okay. What happens if it's not differentiable? If it's not differentiable, well, you can think to use subgradients instead of gradients. But in our case, for choosing one subgradient in particular, we will use the proximity operator. How do we find it? The problem is minimize fx. The optimality conditions in the case in which it's not differentiable, now we have, for example, our function like that. Well, that's a minimum. We cannot say that the gradient in that point is 0, but at least there is one which is 0. Then here, I said, for example, that in the absolute value of 0, what's minus 1, 1? Well, here is 0. It's one of the slopes. One of the slopes is 0, then 0 belongs to the subdifferential in that point. Okay, and it's also a characterization of solutions always in the convex world. Then optimality condition is solution if 0 belongs to the subdifferential. Again, similar to the later case, we can now multiply by gamma and add an x. And here appears identity plus gamma subdifferential. I said that if we can invert that, that's the proximity operator. Then from here, just doing that, x star belongs to identity plus gamma subdifferential of f. And x star, then we can invert that. I said that it's possible, and you have a unique solution of that. And we have that's equivalent to that x, it's equal to prox gamma f of x. Then a characterization also of solutions in that context are fixed points of this operator. Well, again, the same story. We can now find solutions via fixed point or iterations of this operator prox. We just take an x0, apply the operator, and apply sequentially, and we obtain that converts to a solution. And when the operator is good enough for obtaining convergence, it's always for every gamma positive. It's a gamma just positive. You can iterate like that, and you will find a solution. That's a result from Rockefeller-Martinet in the 70s. If the function is strongly convex, we have that the prox is a contraction, and again, you have the Banach fixed point theorem, and you converge very fast. If not, you have averaged, and again, you can have convergence. In the differential case, just for knowing what is the difference with respect to this one, I have not recalled, but I will try to do it. We have an xn. That's this. I didn't invert it. I write just the equation in the case of differential case, and now it's an implicit step. It's not if we can pass the gradient to the other side and take an xn. It's just a gradient step. But now we have an xn plus 1. Then we have an implicit step. We have to solve an equation. We have xn then is xn plus 1 plus gamma gradient f xn plus 1. Then the idea is to find an xn plus 1 that's going in the other direction. We have to find here an xn plus 1 that's going here in the other direction with a step gamma finds xn. That's the idea. That's how to find this xn plus 1 that going in the other direction. You can go to xn. Then it's an inverse relation. Here you have to solve an equation. That's why it's kind of more difficult to find it. And the other case, you are just explicit step. If you know the gradient, you go just in that direction. Here you have to solve an equation. Anyway, in several cases in which it's not differential, you can have that proximity operator and it's explicit. In the particular case of the norm, the L1 norm is a known operator, which is the soft thresholder operator. Then several other cases you can find the prox. Okay, that's the first part of the talk, in which it's just simple. One possibility is go just straight by the gradient, an explicit step. If not, it's an implicit step by using the proximity operator. Yep. Yeah, the subgradient, it's if you take that, the subgradient that you are taking, it's just like that. That's the element of the subgradient we're looking at. Take an it's looking for an xn plus 1 in order to that this one it's in the subgradient. It's a special choice of a subgradient, but also that moves. That's why you have to solve an equation somehow. Even here, if this is the gradient, you have to solve an equation. Here, it's solving a problem indeed, because well, also here, the proximity operator, I said that it's minimize a function. Sometimes that minimizing function, you can find it explicitly. Yeah, but for here, for solving this one, is unique. For satisfying this property is unique. Because you are moving xn plus 1 here and xn plus 1 here. And I said that this operator is invertible. You have only one possibility. Then if you have xn, there are only one xn plus 1 that satisfies this inclusion. Even if here it's a set. No, you don't need it. You just need to solve a problem. Indeed, that's xn plus 1. It's equivalent that xn plus 1 solves. Whoops, it wasn't me. I have the phone there anyway. It's just our mean f x plus 1/2, 1 over gamma half, x minus xn. You have only to find this one is to minimize that problem. For an xn, given an xn, you minimize this problem. This problem has a unique solution. The solution of that satisfies exactly that, and there's only one solution. Even if this one can have many slopes. Yeah? The thing is that it's not that important that inclusion, but the interpretation, and also that for several f's you can find explicitly which x n plus 1 is. And well, if I have some time, I will show you some examples in which a proximity operator is explicit. For an xn, that's the formula for having x n plus 1, just like that. Yes? Yeah. Yeah. Yeah, for this one, it's also averaged. If you have averaged, you have always the same order. If anyway, I said that if you have a little bit more strongly convex, for example, the proximity also is a contraction. You have if you have strong convexity, always you have faster algorithms. If not, just order ones over k usually. Here it's difficult to talk Lipschitz condition. So you can have you have no differentiability. Sorry. The differential case, even with Lipschitz condition, I don't know. I guess you cannot have more. I'm not sure. I'm not sure if you have a Lipschitz condition, you can have a little bit more. Yeah, it's a good question. I will look it forward. Okay. Well, what's happened if it's more complex than that? We have the basic cases. Now, what happens if f can be greater than the sum of two? Yeah. Of course, if both are differentiable, you just use the gradient, differential with Lipschitz gradient. Just use the gradient. But what happens if f is just convex and lower semi-continuous? Can be a constraint, can be an absolute value, for example. But J, it's good enough. Yeah, yes, it's great. It's differentiable with a Lipschitz gradient. Well, in that case, when we have that some qualification condition holds, and we can split here. Well, the sum is convex. It's sure. Then we can the optimistic condition is that 0 is the subdifferential of the sum. Here, there are all the story of qualification conditions. I will not discuss too much over that, but here, the qualification condition holds, and you have you can split the subdifferentials. And here you have just the gradient, because it's differential. You don't have a lot of slopes, you have only one. Then you can write the optimistic conditions that 0 it's in this sum. Well, same story, we can, from the optimistic conditions, to find an operator. What do? We take the gradient and we put it in the other side. Yeah, the minus gradient is in the subdifferential of f. Here's the set, here's just a vector. And here's this one. You can multiply by gamma, and you can add an x. Yeah, and if you forget about x, you have just minus gradient g, it's in subdifferential. You multiply by gamma, you add an x, and you have that inclusion. Same thing, identity plus gamma f, you can invert it, and you have that it's equivalent to be a solution of P to be the fixed point of a composition of two operators. And there are two operators that we know, and it's the proximity operator, this one, and the gradient of J, this one. We compose both, and then it's a fixed point of the composition of gradient and prox. Proximity operator. Then, well, it's interesting. Same questions. And then for finding a solution, we have a forward-backward splitting, in which it's known forward-backward because we have an explicit step on J and an implicit step on F. Yeah, you have that for one function and that for the other function. What happened with that composition? We have discussed that the gradient one, the J gamma J, was averaged when the gradient was Lipschitz. Then we have an averaged operator here and another averaged operator here with different constants. And we, in the preliminaries, we discussed that the composition of averaged was averaged also. Then we have the possibility to, even in the worst case, have a convergence of iterating with this operator, which is the composition of the two later operators. If, in addition, F and G are strongly convex, of course, the first one, it's a contraction, and the second one also. Then the composition of contraction is a contraction, and also you have linear convergence, but we're asking to both to be strongly convex. If not, it's averaged because both are averaged. It's only one strongly convex, we cannot ensure that the composition will be the composition of the operators, I guess. Roberto has a strong
The composition of a contraction that's a non-expansive is a contraction.
and expansive. Yeah, probably I'm mistaken. Yeah, well, yeah, you are right. Let me just verify. Yeah. Why? Yeah, anyway, you have a contraction, you have, yeah, you are right. I have a mistake here. Yeah, if only one it's, you can have the convergence. Thank you, Roberto. Yeah, it's true. I get lost here. Indeed, if only one you have, forget about this line, please. If you have only one, you have also linear convergence. But if both are not, just you have average. Yeah, I did that later. Sorry?
That line is correct. You say that it is enough to have one, F or G, strongly convex. Oh,
not enough, yeah. then the thing is to that. Ah, no, sorry. No, I will do it with this one. It's enough. Yeah, no, it was later doing that in the afternoon. Then. Okay. Then having that, you will converge if one of both after the correction of Roberto, if one of both are good enough, you have linear convergence. If not, just the 1/k. Particular case, just for having an idea of how this works, it's the gradient projection. It's a particular case in which f is the indicator function of a convex closed set. In that case, I will take the same design. You have the function j here, which is differentiable, and you have a set C. We're looking for this point, indeed. Yeah, here's the set. You have the point in which the value of j is the lower. Then how do it like this algorithm? Well, I will take this one. We have xn+1 doing the same thing, and after the gradient of j, you project. You have the projection here, and then that's that's an auxiliary point, and that's the xn+1. Here you take also, you're going in that direction, and you project. Doing like that, you approximate that point. Okay? But if you have another f, well, the design is not that easy, but also works well. Okay. What happens if you have non-differentiability at all? Well, the operator that we can try to say it's easy. Okay, we just compose the prox. If each one is averaged, then the composition is averaged, and the physical iteration converges, and everything goes well. But it's not the case, unfortunately. No, because if it converges to the solution of another problem. It's not the problem that you want. Just analyzing the fixed point iteration is the solution of this problem, which is very different to the other one in the general case. Of course, if you have just two indicators, it's the same problem, but in general, it's not the same problem. How you can look that? If you take x equal prox gamma f, the prox gamma g x, we will call it this one y. Okay, we have y is prox gamma g x, and the proximity operator, we will say that it's equivalent here then, that y belongs to x star plus gamma subdifferential f x star. Yeah, because prox it's, I remember you, is identity plus subdifferential f minus 1. Then we put it on the other side, you have x plus gamma j subdifferential of x. then we have y minus x in gamma subdifferential f of x. And why was this one? We can do the same thing. Then we have x minus y in gamma subdifferential of j of y. Then we have a coupled inclusion. And x minus y in gamma subdifferential f of y. We have that. If we have the sum, we will say, okay, we have just the 0 in subdifferential f, subdifferential of j, but are in different points, in x and y. Indeed, this is the optimality condition of this problem. Okay, if you differentiate with respect to x, you have the first inclusion, and you have the optimality condition with respect to y, you have the second inclusion. Then it's not the same problem. Then what can we do? That was the natural operator to take, but it doesn't work. Yeah? Both. We're without differentiability at all. Neither an G. If one is differentiable, we can take the later algorithm. Yeah, I just discussed it. If one of those is differentiable, you can do that. Yeah. G is in that case was differentiable. If no one of those are, what other operator? I would like to replace the gradient step by a prox, but it doesn't work. Then, well, on the qualification condition, the optimality conditions is this one, not exactly this one. And it turns out here it's a little more involved, the derivation of the problem. But it turns out that that is equivalent to that composition of operators. There's a prox that appear here, then that you can call it set. For example, another point is an auxiliary point. And you have the composition of two operators, we are the reflections. I will discuss just in 2 minutes what a reflection is. But the reflection, well, for a function f, is 2 prox f minus identity. Why is a reflection? Take a simple example. Take a simple example in which f is indicator of C. C, we would just take it's a line. Then what a reflection is, it's, if we have a point x, the reflection of identity is C of x. I'm talking that is twice the prox. The prox in the indicator function is just the projection minus identity. Then the projection is this one, that's BC of x. Twice the projection will be there. So imagine that 0 is here. You have the projection, twice the projection is there, and the minus identity is there. Then the reflection is here. Yeah, the 0 is here, twice the projection, minus identity goes here. That is exactly the reflection with respect to C. Okay, well, if the set is like that, it's not that clear, but it's the same thing, same story. And if it's a function, also that operator is good enough. But it's just non-expansive. Then this one is not more than non-expansive. This one also. Or not. Then we cannot just, for example, take a Z and Z and iterate that way because it may not converge. But the Kanusevsky-Man iterations converge. What the Kanusevsky-Man is just to compose with the identity, to have a combination, a complex combination, the identity and the operator. If we do that like that, you don't take this one as the x plus 1, you take something in the middle. And we do the same, we take something in the middle, and we are converting to the fixed point of the rotation like this. And if we check just the rotation, the only fixed point is 0. Then that's allows us to solve, and that's the Douglas-Rushford splitting. Douglas-Rushford splitting, what it do is takes the Z0 and iterates by doing a Carson schema iteration of the composition of the two reflections. And that's when that converges to a fixed point of R, composition bars, but that's not our solution. The solution is props of that. Okay? Then we take the props and that's solution. That's an algorithm for solving the problem in which you have two non-differentiable functions. Then just an example of what the algorithm do in the simplest case. In the simplest case, we have just C, F is indicator of C, G is indicator of D. We take just two lines. And what the algorithm do, take a Z0, take the reflection onto C, take the reflection onto D, and you take the average. Take the 1/2. Again, and that's this next point. Take the reflection to C, take the reflection to D, and take the average. Again. And like that, you are going to the solution. Okay. Well, it's not this one, the good iterates, but are the in that case are the projection onto in that case D. Okay. This one is really D, and you're having points here and here that go into that solution, which is the common point, the only solution is. Okay. What happens if we compose with a linear operator? It's even more complex. Now you have the F, the G, but a linear. If J is smooth, in the same story, F it's just convex and J is Lipschitz. Well, if J is smooth, it's not a big problem because you just defining H just the composition. That's differential because J is differential. The composition of the linear operator gives you the gradient is just this one. And that's also Lipschitz. Yeah, the Lipschitz constant will be norm of L after there's another norm of L that will appear. And you have norm of L squared and the constant of the Lipschitz constant of gradient. Then you can just use the forward backward splitting in that case. The problem is what differential. Because of the composition is not easy to handle. In some cases in which J is have some special structure, you can find that explicitly, but in general, it's not easy. Then we will like to exploit to separate the operator L from the operator G, so the props of G. Then one idea which is very old is to use the momentum Lagrangian. What this idea is to add an additional variable instead of Lx. Lx, you say that it's on y, and you say y now. Have another. Now you have a constraint, a linear constant. Multiply and take the Lagrangian, but the Lagrangian is not good enough. Then we take an as the non-square. If you have a solution of this one, also you have a solution of the original one. By using the momentum Lagrangian, there is under some clarification conditions, you have that that point is a saddle point of the momentum Lagrangian, and doing some alternating minimization maximization of the Lagrangian, you obtain the classical alternating integration method of multipliers, in which you have these three steps. A minimization, the first one, we have x, y are the primal variables, and they use dual. The momentum Lagrangian, instead of minimizing both, minimize one first on the x, after to the y, and then an optimization of the multipliers. And you do it again. What is one problem of this algorithm? That is that if f is not good enough, it's difficult to compute the first step. Because here you have an x applied to a matrix. Then if you have the numerical conditions here are to invert the x, it's difficult. You will have an L star L or L transpose L to invert, and some differential here in general. If F is quadratic, it's just a big matrix to invert. But if not, it's difficult to have this step. The other steps are easy because the second one that's computable. But we would like here to have explicit step, something like that, an L and after a J, something like that, which is difficult to solve. Then here it's a prime modular approach that allows us to do that. The idea is to take the problem and under qualification conditions. A solution here, it's 0 of transpose. Here appears the subgradient of G of Lx, and here you can take an U here. You take a dual variable of the subdifferential J in Lx. If you take an LU here, you have exactly that. Here nothing is smooth. J is not smooth, F is not smooth. Sorry, yeah, that's should not appear. The smooth part, we will say that's just for a value. Yeah, here it's just a mistake. Where we are asking the more difficult case. Then the idea is to take an U here and a series in so differential L transpose U. Well, here is the part of the preliminaries that probably you have completely forgot, in which if U is here, you can invert the subdifferential. Appears the subdifferential of the differential conjugate of G. Then you can LG, it's in the inverse of subdifferential J of U, which is the subdifferential of the differential conjugate. And the other one is keeps like that. Finally, we can put something like in a matrix form. It's just a way to write it. We have here, that's because of this diagonal. It's not difficult. I will not do it, but it's a property that we have a function f of xu, which is separable. Well, the subdifferential f of xu is nothing but it's a differential f of x, scalar product of this. Then you can put it, if you like that, it's a differential f of x, the conjugate of x. Then you can say the operator A here as the subdifferential of a convex function. Here is the sub. Yeah. Then the first one is good, but not good enough because the first one is a differential, but the second seems not to be and is not the gradient of any convex function because it's not symmetric. Yeah. Then in the product space, A is a subdifferential, but B is not the gradient of any convex function. Anyway, B is a nice operator, which is it's a nice operator. I just will say that it's a monotone operator. I will say a little bit and a bit more at the end. And you can try to do something similar as we have done before. To compose, apply the operator B here, like a gradient step, and after the operator A, implicit step. But because this is not just a good gradient, you have to have a kind of correction, okay, correction of the particles. And the convergence in this case is obtained by a quasi-non-expansive operator. It's a special case, it's a more general case of an expansive operator that involves B and cross. Okay, here I will not enter into details, but there is another operator here that allows us to ensure the convergence of this algorithm. The other classic algorithm that can solve that is Chamberlain, in which if you say it's something similar to the previous one, but instead of here you're having here you can parallelize this simultaneous step. You take the n and you take the n plus 1. Here it's an alternating version in which you take uk plus 1, the k plus 1 enters here, and you have the x and k plus 1. Because of this step, x bar that goes here, you are using some information from the past. You are using here when x bar k enters, they're taking xk and xk minus 1. Okay, then you are using information from the past, and that allows us to have the convergence. Indeed, one brother of mine, academic brother of mine, who shows that that algorithm is a particular case of the proximal point algorithm, but with a special method. Because everything that I talk here is not just RM, you can do it in any Hilbert space and take the different methods. Then by doing different methods, this algorithm is just the proximal point that I showed you here, but with a special method. Another explicit approach is the Entente, which is more similar to ADMM that I showed before, but only with explicit step, and it's very good. Okay, just for finishing, I think it's we will talk some perspective. That's a little story of what the algorithms come, but that goes very far. For solving a problem where more than two functions appear, you can use product space techniques. The idea is to change. Imagine that you have a problem like that. You minimize its sum ix, several functions, all of them convex. Well, you have not two, you cannot apply any of the algorithms that we have discussed, but this can be settled as minimize x1, x2, imagine this is n, until n is n. The sum of I1 is I. Here it's not the same because we have split all the variables, but if we have an additional constraint in which the vector x1 is equal to x2 equal to n, it's good. Then what's happened? This one is convex, but in the product space because it's separable, and that is a convex closed set. Then you can see like that, like minimize a big X there, a big Fx plus indicator of that, we will call it vector subspace of X. And here you have two, and you can use everything that we have discussed before. But in a product space, now the dimension is higher, but allows us to solve it.
How about these examples? There's a bit that you can talk about the DNN in 3 blocks.
There's any problem about it because we'll discuss in so much. Yeah, it's not a problem because if you look at here, the dimension is not a problem. Imagine that you have 3 blocks, L1 x1, L2 x2. Your problem, if I remember well, is imagine minimize fx plus gy over ax plus dy equals 0. I don't know, something like that. Or 3, no, that's 2. Okay, here. CZ. So that's, I don't know, HZ. Well, in that case, it's just a convex function f of x, y, z in the product space. And it's an operator L of x, y, z in the product space. We can also apply everything that is done here. It's not a problem at all. The thing is that in ADMM that we are using, you need, the main problem is you need to invert the matrix. And the first step here, you need to invert this matrix to solve it. And that's a difficult part. And when everything is split.
Actually, there's a paper by Mansbergen, by IIIO, that they show that the ADMM is with 3 blocks. They show a counterexample and it was not correct.
No, I'm not doing that. I'm not doing that. I'm saying that it is difficult. I'm doing other technique, which is the prime order approach. And well, that's my bad.
It's a different approach.
Here is an operator. We take the 3 variables that we are interested in, but everything is just one linear operator, but in a higher space. And in this higher space, you have that function which depends on 3 things. But also, it's just one function if each one is R in a 3-dimensional space. That is the center N. Then if you say anything in there, the algorithms are longer in the sense that you have several variables that you have to but the essence is the same. Yeah. And that's that I propose you to see a little bit. Well, that's one of them, but also some of those in which you have just explicit, that's the important thing. You have an explicit step on L. Here in that case, in your case, you just take A, B, C of each part. And here you have the transpose, this is easy to compute. And you have the proximity operators of the functions here. And it's not difficult to compute. Okay, just to finish a little bit. Well, if it's, that's the first thing. You can also take several variables, several functions, and also that works well. All the methods that I present, I take just a simpler cases. But you can there's that instead of gamma, you can have a gamma n. And sometimes the choice of gamma n allows us to have better convergence, as we will talk about next week. Also, Hilbert spaces are allowed instead of just Rn. Some other errors, if you have its proximity operator, it's difficult to compute. You can add a little bit of error if it's summable, which is also difficult to have that. If it's a little thing which is better, that also will converge with the same speed. And variable metrics that allows us to understand several algorithms which are now sometimes as special cases of algorithms, classical algorithms. Also, and that's I talk a little bit, but I didn't want to enter into details. It can be also applied to find zeros of maximum amount of operators. So differential is one maximum amount of operator. That's its used to optimization. But also there are a lot of other maximum amount of operator that allows us to solve subtle problems, then the ranks also. There are some games. There are other special games, but Surzan is the main class that can be settled as a maximum amount of operator. Partial inverses, then constraints involved in vector subspaces, and some PDs can also enter into the maximum monotone structure. Then all these algorithms in which you have a subdifferential, you can change it by an A, which is A maximum monotone, and also everything goes. Then in Go applications, I will not enter a lot of details because my part was the optimization part. Then probably I will talk things that I don't know well. But I was working with Francisco Cid and Dante Calice, one from France, another one from Austria, on midfield games where were introduced the last regions, and models a game in which you have a number of players that tends to infinity, and the number of players that indistinguishable. The limiting behaviors collapses into couples PDs in which you have the cost function of one small player and the distribution, because they are not atomic players. You have a kind of small players. You have a distribution of the actions. Well, finally, after some optimization procedure, the couple PDs can be seen as an optimization problem. And that's the part in which I enter in. And the minimization problem, I will talk about what is this one. That's an optimization problem with an integral of two. The thing is the two convex function. This one is convex, and this one is non-differential, and with a linear constraint. Here you have just linear. The Laplacian is linear. The divergence also. So variable W that appear here, and well, because it's a probability distribution of the actions of the players, the sum is the integral is 1. Then on the F, it models the influence of other players in the choice of each player, which each one is indistinguishable. The function BQ appearing here is this one, and even if it doesn't look like, it is convex. It is convex, and because of the plus infinity here and the 0, it's a tricky convex function, but it's convex and there was made continuous, fortunately. And we try to find its prox, and the prox is computable. Just need to solve a quick equation for each parameter. Here is an infinite dimensions, but we solve it after a discretization of the problem, of course. And it's just solving a real cubic equation, and the constraints are a phi linear. All these concepts enter into our setting. This convex function, one differential with the other isn't, and a linear constraint, then convex. Composed, of course, with linear operators, the Laplacian and the derivatives. And we use prime method approaches. We use Chomolkov, the first that I introduced, and Centebu. And now we are in the numerics, and they're working quite well, even if it's only first order, as I told you. I didn't say, but the variable metrics allows us also to use second order. Well, some references, and well, thank you very much for your attention.